So let me just summarize some of the main points we saw last time. Was everyone here last time? I understood that it was not recorded, so if someone was not here, everyone was here. You were not? Okay. So let me recall what was discussed yesterday. So we started by revisiting what is perhaps the simplest possible flow. It's a trivial flow of a free theory. That is one free massive scalar. And we saw that at very high energy, it becomes effectively massless. And at very low energy, things decay exponentially, and so there's nothing. And so in equations, we can write a propagator of the scalar. And then we showed that at very large distances, it decays exponentially. At very small distances, it explodes with a power law. And so this power law behavior, when we are at very short distances, we just see a massless scalar effectively because it's very energetic. And it's a two-point function of a scalar operator in a conformal field theory with dimension which is half whatever is in the exponent. And that was what we expected from dimensional analysis, from just looking at the Lagrange. Okay, then we asked, so what's the definition of a CFT? If I want now to look for more general CFTs, not this one or the free massless scalar, but a generic CFT, what is a CFT? A CFT is a theory which has this local dilatation invariance. Namely, if you give me a correlation function, and then you locally change the metric of your spacetime. So you apply a dilatation here, you contract a little bit here, you contract more there, you do nothing over there, and so on. Then you change the metric from G to G times a local dilatation at each point. And that should give you the same correlator up to some simple factors by how much you dilate at each point. Okay? The most trivial example is you just make a global dilatation of everyone. Then you should just get the total dilatation to the total power of dimensions. Right? That, of course, works here. If I make a dilatation, r goes to lambda r, I just pick a factor of lambda to this power, and this power is indeed the sum of the two dimensions. So, of course, it works. Now, this definition of what a CFT is, it implies this condition here, it's weaker than this, but it implies this one here, where now we have two correlation functions, both in flat space, and what sits in the left and the right hand side is a correlation function that differs by a conformal transformation. That is a transformation of points, where I send some points to another set of points, where the property of this transformation is such that under this transformation, x goes to x tilde, the metric for x tilde is the metric for x up to rescaling. Right? So it's this active versus passive transformation. I can do an active transformation of changing the metric, or maybe that's passive because it's easier to change the metric, or I can do an active transformation of moving the points around. That requires more work. I need to drag the points. So let's call that second one active, right? And it's the same thing. You should not do both. You either do active or passive. If you start doing both, you are doing nothing. So one example of a conformal transformation was an inversion. Under an inversion, a distance transforms in a simple way. The metric transforms in a simple way. It is just an infinitesimal distance. And so this is a local by how much points are dilated if you do an inversion. Right? Now, another implication of that formula there was that we could now relate a conformal field theory in flat space, where here I'm drawing spheres of bigger and bigger radius. I'm doing it in a plane, so they are circles, to a conformal field theory in a cylinder. And as some of you asked, and I'm going to explain a little bit later today, but I can anticipate again, we put the vacuum here, and we put the vacuum at plus infinity, and all we do is we put operators at some finite values, like one here, another one here, and that corresponds to putting nothing at the center, putting one at the center, and putting one at infinity. You do nothing. You put nothing. Don't put an operator there. Okay? And that's why there was no issue with topology. That some of you were wondering, this looks like a plane, this has a hole in the bottom, in the top. What's going on? Is it the same thing or not? It is the same, because we just put the vacuum there, so it's trivial. And this correlation function we derived because we saw that we could map flat space. We can write it as a cylinder like this. And so we learned that this is the two-point function of two scalar operators in the cylinder. So that's what happens if you study some theory on a cylinder. Okay, so now today let's continue exploring some consequences of this master equation, and in particular of this equation here. Okay, any question? Okay. So first, let me start with something rather basic, which is let's analyze in more detail the structure of two-point functions. So I have an operator of dimension delta 1 inserted at some point x1. I'll do a conformal transformation. O2 x2 tilde. I'm going to write that equation again, and this is equal to omega to the minus delta 1 of x1 omega to minus delta 2 of x2 times the correlation function O1 of x1, O2 of x2. The transformation x and x tilde could be an inversion, for example. It could be any transformation. Now, the first observation here, delta 1 and delta. The first observation is that this correlation function should be invariant, should be the same if we just swap x2 and x1. This is just a rotation by 180 degrees. I have 2 points, x1 and x2. I can swap the 2 points, x1 and x2. That's just a rotation by 180 degrees. But this, if you look at the right-hand side, is quite non-trivial, because this symmetry will not work if I have general deltas. And so this implies that this is equal to 0 unless delta 1 equal to delta 2. Now, if delta 1 is equal to delta 2, then we conclude that the correlation function O1 of x tilde 1 dot 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 is equal, by dot 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 is just the second term, to omega of x1 times omega of x2, everything to the power minus delta, both of them, times the correlation function O1 of x1, O2 of x2. Right? But now we can say that I pick here x1 equals 0, x2 equal 1. I decide to do it. And here I write that I will consider a transformation where x tilde is equal to lambda x. I make a dilatation such that it sends 0, 1 to 0, r. Right? So with lambda chosen to be r, the separation between the 2 points that I want to get. Yes?
Did you say again when it's 0?
We choose. Sorry?
What,
So what I want to do is the following. I want to pick this point, 1 point at 0, 1 point at 1, and say that there is a conformal transformation of this, which is a very simple one. It's just a dilatation. That 0 goes to 0, because 0 times 0 is 0, but 1 times dilatation goes to lambda. So I want to apply a conformal transformation where these points becomes now 0 and lambda. Right? And so because I want to call this a separation between points r, I want to identify lambda with r.
this is why the correlation function is 0?
Ah, sorry, you meant the previous argument. Sorry, the line above. Sorry. No, the correlation function needs to be the same if you swap x1 and x2. Right? So this correlation must be invariant under swapping x1 and x2. But this object here is not, because here I have power delta 1 and power delta 2.
Oh.
So the only way to make it invariant is by setting the deltas to be the same. Otherwise, I need this to be 0.
Thank you.
That's it. Okay, so now here it's another argument. I'm saying, okay, now they are equal. And I say that I start with points 0 and 1. Then I can say this is just some normalization. And then I apply a dilatation that puts now 0, 1 at 0r, which is what I want. But what's the weight I pay here under this dilatation? Well, omega is obviously equal to lambda, which is nothing but r. And so we conclude that this correlation function is equal to some number, d12. It can be this correlator here at 0 and 1, just a number, divided by r to the delta. And that's what you wanted to show. Right? So, to the 2 delta, yeah. Right, each 2 delta. Thank you. Right? And that's exactly what we want us to establish. So notice that here, what we did, one way of deriving this result, another way would be, which is more or less what we did, but let me stress that this is a logic that we could use. The logic is, if you want to get correlation function with some point at x and some point at y, you can say that this is equal to a conformal transformation of a configuration where 1 is at 0 and 1 is at 1. Because you can always map any points to 0, 1, right? It's enough to just, first you make a dilatation. Let's do it from 0, 1 to any points, right? First you start with 0, 1, then you make a dilatation till you get the right separation. Then you make a rotation till you have the right orientation, and then you shift such that you have where you want to be. Right? So you can always find this conformal transformation. And therefore, we can write that the correlation function from x and y is just whatever that conformal transformation is that sends 0, 1 into xy, evaluated at x to the power minus delta, times the same thing for y, times a number, which is what the correlation function gives at 0 and 1. Right? And so you know, just from the pictures, that the formula exists and that you could find it by just working out the omegas. Right? But then, instead of doing it, you just guess the result and you write the result because you know it exists, you know it's unique, right? So you can just guess it and you write it down. Then all you have to do is check that it transforms properly. Right? So this is a solid argument. I'm not cheating, right? It's honest. First I prove existence. It's here. Now that I prove existence, guessing is science. Right? Then I guess. I say the result is 1 over r to the 2 delta. Then I check. It transforms well under inversions. It does, so it's good. Right? So guessing is okay if you prove existence before. Then it's science. Right? So it's good. The argument is mathematically solid. Okay. Now, this is interesting because we can now apply this argument for 3-point functions. Right? So for 3-point functions, similarly, right? We know that any 3 points are equal to a conformal transformation applied to a point at 0, a point at 1, and a point at 2. Say a point at 0, a point, something like that. I can always put 3 points at 0, 1/2, 1, and then map it to any points x, y, and z. Right? Is this clear? You have seen this. Does someone want me to explain, or it's clear to everyone that you can map 3 points to any 3 points? Because it is true, we know that this correlation function, the correlation function for positions x, y, and z, is again just given by a product over whatever weight I get when I transform 0, 1/2, 1 into x, y, z, evaluated at the position, let me put here, okay, evaluated at capital W to the power minus wi minus wi, product over I equal 1 up to 3, where wi is just x, y, and z. And the correlation function will be equal to this times whatever the correlation function is here, which would be a number. And that number, we can call that number C, and we can call it C1, 2, 3. Right? Now this shows it exists. Right? We just showed it exists. Right? It's just enough. Find the transformation that goes from here to here, compute the omega, and this is the result. Now we can guess. We can just write what the result is and check that it has the right, that it transforms correctly. And so the result for the correlation function of 3 operators, O1 of x1, O3 of x3, is equal to C1, 2, 3, now that we showed we could find it. And then we have to divide by x1 minus x2 to the power delta 1 plus delta 2 minus delta 3. Then x1 minus x3 delta 1 plus delta 3 minus delta 2. Finally, x2 minus x3 delta 2 plus delta 3 minus delta 1. Okay. So tomorrow, when I will summarize this part of the lecture, I will show you how to compute these omegas in a simple way so that you recover this doing the honest computation of these omegas. Okay? But today it's enough to know it works. Why does it work? Because it's a good guess, because we can just check that it transforms well under inversions, for example, which is the only non-trivial one. All other ones are trivial. You can just. Okay? And inversions, to check that it transforms nicely, you just use the property of inversions here to check that it goes through inversion. So it exists, we guessed it, it transforms nicely, so it is the solution. Okay, tomorrow we can go through this change of variables. Once I can write it down before the lecture starts so that we don't lose too much time, and we can see this in detail. Okay. And so this is the form of a 3-point function in a CFT.
Pedro?
Yeah.
How would you transform those random 3 points into 0, half, and 1? Because it seems like the angles are changing, right?
That's right. But conformal transformations to change angles.
So if it's only an overall factor, the angle should change.
Sorry?
So you have a metric that goes to omega squared times the metric. So how would the angle change?
Infinitesimally, no. For well-separated points, it does. Yeah. Okay, but let's do it then. Let's transform points into 0 and half 1. So let's do it in this direction. X, Y, Z goes to this. So let's see how we will do it. So we start with X, Y, and Z here. First, we apply a translation such that we get, let me use some symbols like this. Let me use a point for X, a circle for Y, and a square for Z, such that we can keep track of who is who. Then first we apply a translation such that what was at X now is at the origin. This guy is translated, is at some Y minus X, and the square is translated, is at some Z minus X. Right, now we have 1 point at the origin, 2 at some finite points. Now we apply an inversion. An inversion, the circle is here, this is here, and this point now is at infinity. Right? I'm not going to write the labels, I'm just going to say I applied an inversion here. So here I applied translation, and here I applied an inversion. Now that I applied an inversion, I can apply another translation so that this circle here is at the origin, the square is at some value, and this point continues to be at infinity, right? Infinity plus translation is still infinity. Now we can apply a rotation such that this point is at the origin, the square is in the same direction, and this guy is at infinity, right? So this is still the origin. Now they are aligned. Then we can apply a dilatation such that this is at the origin, this is at 1, this is at infinity. So before they are still at a general separation here R. Right? Now we are at 0, 1, infinity. Now we can apply a translation and make this at 1/2 3/2 and infinity. No, let's apply a bigger shift so that this is at 1, this is at 2, this is at infinity. Right? A translation. And now let's do an inversion such that 1 continues at 1, 1/2, 2 goes to 1/2, and infinity goes to 0. So 2 goes to 1/2, and 1 is 1. Right? So we start at any points, we do just a few transformations, and we go there. Okay. Yeah. Just anticipating, each time we do a transformation, we could relate the correlation function in steps, right? We could say this one is this one times a factor. This one is this one times a factor. So the factor that we get in total is a product of factors, one for each step of the transformation, right? In other words, the conformals group is a group. So you apply many times. So which ones would be interesting to compute? What factors would we need to compute? Well, this one, there is an omega here. Not here, translation as just omega equal 1, there's nothing there. So there is an omega to be computed here, or inversions, that's very simple. Here we translate, nothing to compute here. Here we do a rotation, nothing to compute here. Here we do a dilatation, so there is an omega to compute here, or this dilatation. Here we do a translation, nothing to compute here, and here we do an inversion. And so there is another omega to compute here. So all we have to do is say that omega is a product of 3 omegas. One for this dilatation step, just multiply by some simple factor. One for this last inversion, one for the first inversion. Okay? So if you work it out, you find out that the product omega times omega times omega at the location x1, for example, is equal to x2 minus x3 divided by x1 minus x3 times x2 minus x1. Okay? That's what you get if you multiply the etc. for the other 2 points. And now we are done. You see, you just take this product, these omegas, evaluate that x1, and you raise this to the power delta 1. Similarly for delta 2, similarly for delta 3. Then you get this formula here. You see, that delta 1 is raised to this x12 to x13 and over x23. So it's exactly the inverse of this factor here. If it's not the inverse, it's because I forgot to flip it. But it should be whatever makes this formula correct. Okay? And so, okay, so now I don't need to do it next time. This would be the simple computation. Right? So we would just compute this quantity, evaluate it at x1, and get this factor. Evaluate it at x2 and x3 and get similar factors. And then we know this product here then gives precisely the space dependence that I wrote over there. Okay? And it's simple to compute these factors. You see the inversion one you got, and so on. It's only slightly subtle because you pass by infinity. And so, anyway, if you want, you can ask me tomorrow, and I can show you this subtlety with infinity. If you have trouble reproducing it at home, so try to do it at home. And if you have trouble because of infinity, you can come to me and I can show you my notes. Okay, very good. So we are done with 3-point functions. So finally, we saw that right now all we have right now, I forgot to say something trivial, which again, all these things I'm assuming they are reviews, so but maybe said in a slightly different way, but just for completeness, let me emphasize that this d12 we can just set to 1 by normalization. Right? We can just normalize the operators just that the 2-point function is 1. Once you do it, now you fix the normalization. Now this number C123 is physical. Right? Because you fix the normalization from the 2-point function. So far, our CFT, our conformal field theory data, the kind of numbers we need to know, is equal to a set of dimensions, delta i's, and structure constant ci, j, k. They are everything you need to describe 2- and 3-point functions. You need the spectrum of the CFT, which is what we mean by knowing the 3-point functions, and the dimensions of the CFT. Right? So this is enough so far. And with this CFT data, we see that we get all 2- and 3-point functions. Okay? Now the claim, and we are going to get there today, but not immediately, but the claim is that actually this gives us all n-point functions. If you know the set of deltas and c's, you are done. You solve the CFT. You know all correlation functions and not just the 2- and 3-point functions. Okay. Again, you have seen this probably before, but we'll review it again today. Okay, so, but first, let me note that the form of a 4-point function, O1 of x1, O4 of x4, is no longer fixed by symmetry, for sure. Why not? Because imagine even if all of them have the same dimension, all operators are identical, they all have delta I equal delta, even if that's the case, then I can write something that transforms properly. Here it is. I will just write for you. x1 minus x2 to the 2 delta, x3 minus x4 to the 2 delta. Obviously, this transforms correctly, right? Because it's like the transformation of a product of 2 2-point functions, and each of them transforms correctly. Right? So this transforms correctly for sure. But now I can multiply this by any function of what are called cross ratios, which are the following. Let me write it. x1 minus x2 square, x3 minus x4 square, divided by the same thing, swapping a few x's. And there is a similar one here. There are 2 cross ratios. And this are called, as I said, cross ratios. And they are invariant under conformal transformations. Right? And how do we see they are invariant? Well, rotations is obvious, translation is obvious, dilatation is obvious. The only one that's slightly not obvious is inversion. But inversion, each distance picks factor of x1, factor of x2, factor of x3, factor of x4, and so it cancels with the ones downstairs, so it's also a symmetry. So inversion is the only one that you need to look and check that you have the same number of x's up and down. All the other ones, it's obvious that it's invariant under dilatations, etc. Right? And so because this is invariant, this object transforms nicely whatever function f I put here. Right? And so I cannot just fix it by symmetry, contrary to 2 and 3-point functions. That's an equivalent way of saying is that it is no longer true that I can map x, y, z, w to a point 0, 1, 2, and infinity. That's no longer true. I cannot do it. Right? And the counterpart of not being able to do it is there is a remaining function. Yeah.
Can we apply the same argument in the 2-point function, saying that delta 1 must be equal to delta 2? Can we apply this for 3-point function and more, so that all the delta a are equal to the same delta? Like my question is, when I say the CFT data are given by the delta a and theCijk,
Yeah.
are we actually saying that all the delta a are the same?
No. No. I'm saying that if you give me a table, a list of saying this CFT has operators with dimension delta 1, which is 5, delta 2, which is 5.3, delta 3, which is 7.2. So you give me a list of deltas and a list of 3-point functions, C1 to 3.
Okay.
That list of numbers, that table of numbers, of course, gives me all 2 and 3-point functions, right? Because if each 2-point function, I go to the table. Each 3-point function, I go to the table. I'm saying that it gives you all correlators. Okay, so again, there is still a function. So here we have interesting dynamics, which is good, which means that different CFTs could have very different behavior, totally different depths. Some conformal field theories are dual to gravity theories, as we are going to see in detail throughout the course. So those have some behavior for Fs. Some conformal field theories are related to magnets. They have the completely different behavior for F, right? So different CFTs with very different physics will have very different Fs. But all CFTs somehow are fixed once we give this CFT data. Yes?
Should your denominator have an x4 somewhere?
Yeah. Good. Thank you. Good. Yeah. Thank you. Okay. So now let me discuss a little bit more of this map to the cylinder. We can do it here, which is going to be relevant for and let's discuss a very important idea, which is the operator product expansion and relatedly the operator state correspondence. Okay, so so the idea is, let me repeat what we saw above with cylinder and not cylinder, that if I have a CFT, I can consider a sphere, and I can consider 2 points that are here inside. Say one point is here, one point in here. So these points here are inside the sphere. And this is equivalent in the picture of the cylinder. I have a cylinder. I have some sphere. And then I have 2 points that are here below some time t. That is related to the size of that sphere. And so here I have these two operators, an operator O1 that, okay, maybe, sorry, one of them let me put, okay, doesn't matter. It could be, say, O1, one of them could be at the origin, one of them, the other one could be at some location X. All right? And you put these operators here, and then you are doing a path integral in the presence of two operators inside the sphere. Right? So you do the path integral with two operators inside the sphere up to some sphere. That's equivalent to saying I do the path integral starting at -infinity, evolving it, passing by operator 1, then by operator 2, and then I evolve it and I stop at time t. And so when we stop at time t, in this time slice, at this instance of time t, I should not draw it like this. I should say here, which is the same as at the sphere, we have some state, psi. We do the path integral up to psi that defines a wave function at psi. Do you agree? Right? If I do a path integral up to here and I stop here, this defines a wave functional here at some fixed time. So we do it radially and we have a state, a wave function at some radius. Or if we do it in the cylinder, we have a wave function at some fixed time.
So the path integral is summing over all. Usually we do sum over all size of the fields. In this case, what is the path integral over?
Just the integral over fields, whatever fields you have of your theory. And then you are doing radial quantization. So when you put your fields implicitly, there is some radial ordering of the operators, but that doesn't matter, right? And so you just have your, so here, it is literally just, you just integrate over all your fields. Say, let me describe it something like this, phi. Then I have operator 1 at some time t1, operator 2 at some time t2, e to the minus the action. I integrate all the way from -infinity till time t, where at time t, at t, my field phi is equal to some capital phi that will be a function of n, right? So I fix at time t and I say here there is some profile that depends on n. And now this gives me a number that depends on this phi, right? So this is nothing but the functional. I have to write a fancy psi, right? It's a functional that depends on whatever profile phi I put at n. Right? And this is what is called a wave function, right? Or a state. Right? And so putting these two operators will give me, I start from -infinity and I evolve, I pass by these two operators and I get a state. Right? If I put just one operator, I pass by this operator, I get a state here. Similarly here, we can evolve here, put some state on this, put some wave function on the sphere, and we get the state. Right? And so this map, operator to state, is simple to explain. You just evolve the path integral, and we generate some state outside where you put the insertions of the operators. Yeah? So this, you can think of this state as evolving the path integral forward. Right? Then you put some operators, you generate some state. Now, you could imagine now taking your state and evolving the path integral backwards. You start with some functional. Now the function is your initial boundary condition, and now you evolve backwards. Right? Now what happens? Well, you just have your state. Right? How do you evolve a quantum mechanical state? You just decompose your state, right, into all possible energies, and evolve it down. Each of them, e to the minus energy, corresponding energy times state. So you just evolve down all the states. And so you make a decomposition of your state into all possible states of different energy, and then you evolve backwards. Right? And so now that you evolve backwards, it ends up saying that this state I can evolve backwards, and it corresponds to inserting some state here at minus infinity. Or if I do radial evolution, it would correspond to putting a state here at the origin. And this is the operator product expansion, that these two operators, I can write them as a sum C1 to k times OK at the origin. Which is the usual statement that if I have two operators, if I look from far away, it looks like just one operator. Or two or three. It's like a charge plus dipole plus quadrupole, right? When I look from far away, it looks like I can replace those two operators by a bunch of effective one-point operators. Right? And so we can, right? So in other words, we start with this. If I evolve the path integral backwards now instead of forward, then what I end up is I have my cylinder, and I evolve the path integral here backwards, and I end up saying that this is equivalent to putting some state here, some sum of Ci psi I at minus infinity. Okay? So this is the usual thing, right? So imagine this is space, and here it's time, evolving up. And what I'm going to do is in usual quantum mechanics, nothing fancy about ADS or CFTs or anything. I'm just evolving in time, and I'm going to put some operator here, like some rock, and the state hits the rock. Then it hits something here, I don't know, some laser. Then it goes on. Now up there on the ceiling, it's a linear combination of eigenstates. So I could also just evolve it backwards and prepare a better state in the floor. That will give the same evolution there. But that state, while before it was a boring vacuum and then there were two operators, now instead that state is a big linear, an infinite linear combination of all possible eigenstates. Right? Because acting with operators is something very messy. It will have overlap with all states. And so in general, that's what we see here, that I have two operators, O1 and O2, and they are equal to an infinite sum of all possible operators with some coefficient.
So evolving backward, we don't see the operators now.
Right, evolving backwards, now we don't see the operators, right? Because I'm just, it's like in the previous example, right? I put a rock here, I put a laser here, I get a state up there. Now I forget about what generated that state, I just take the state and I evolve backwards.
And this interpretation of time is slightly confusing to me. In our case, the tau that we defined was some log r or something like that. Yeah.
That's right.
So how are we interpreting that as?
No, but it's time, right? That theory there is a cylinder, so it's as time as it can be, right? What is time? Time is when you say your space-time is r times whatever. If it's r times a Calabi-Yau, it's particles moving in a Calabi-Yau, and r is time. Here we did it. It's r times a sphere. So it's a cylinder, right? So now if you are worried about the signature, you just flip r tau to I tau if you want to really have an honest time, right? Now we have an Euclidean time, which is fine. You just evolve instead of e to the IE, you evolve e to the minus beta e, right? But that's not a big deal.
Pedro,
Yeah?
your quantum mechanics and analogy looks really nice, but this operator, local operator state correspondence doesn't happen in quantum field theory, right? It's because of CFT that you have a local operator.
No, it depends. So the step, what we gain in a CFT is that I can go back and forth between flat space and cylinder for free. It is not true that in a quantum field theory in a flat space is not related to the same quantum field theory in the cylinder. They are not trivially related. Here they are. And so if I like thinking that I have points together and I replace by an operator, I can. If I like to think in terms of time evolution, I can. I just jump back and forth between the two. That I cannot do in a general CFT, quantum field theory. But if I have quantum field theory on the cylinder, then everything I said is correct. If I have two local operators, they generate a state. If I have a state in any quantum field theory, I can evolve it backward and generate a state. All that in this side of the picture, it is just usual quantum mechanics. It's true always. What is not true is the back and forth between flat space and cylinder. That in CFTs, it's the same thing. Just pay a bunch of conversion factors, and you can really go back and forth and think whatever makes you happier. You cannot do it in usual quantum field theory. So now, when we write so when I say that O1 at x, O2 at 0 is a sum of operators, we can say more precisely that operators in a CFT, they are organized by primaries and descendants. Let me write it down and you tell me if it's clear or not. And I can decompose this as a sum of primary operators OK. And then I have some constant ck that could depend on the location times the operator OK evaluated at the origin. But I can have descendants. So what are descendants? Descendants, here we are thinking of derivatives of the operators, right? So does everyone know what descendants and primaries are? I don't want to re-give all the CFT course. Who was not in the CFT course? Okay, so then I should say maybe just a few words. So the point is the following, that right. If I have an operator O with dimension delta, then derivative of O as dimension delta plus 1, because derivative has 1 unit of mass. Right? That's pretty clear. If you compute 2-point function, O with O, now take derivative of that correlation function, you just increase the powers of 1 over x minus y. And so whenever you have a CFT, you have some operators that have dimension delta, and then you have a tower that have delta plus 1, delta plus 2, delta plus 3, which are what are called the descendants. So there is one operator that is not of the form of derivative of something else, and then this guy is called the primary. And these ones, that would be 1 derivative, 2 derivatives, they would have delta plus 2 dimension, etc. These guys are called the descendants. And because they are just derivatives of primaries, if you know correlation functions of primaries, you know correlation functions of these guys, because you just take derivatives of the correlation function. And so it's enough to sum over primaries, and then you have the primary OK, and then, as I said, you have the descendant, which is just d mu of OK. Again, OK, the definition is it's an operator that is not derivative of something. And then this guy would come with some constant C mu that could depend on K and on X. And then also evaluated at the origin, plus, and then some C mu nu that could depend on K, d mu, d nu, OK evaluated at the origin, plus dot dot dot, an infinite set like this. And you would have one such term for each primary, because if you have a primary, you also have the descendants a priori. Right? So this picture here, as we said, is equivalent to saying that I start with 2 operators. That gives me a state here. But the state here I can write as a sum of Ci, psi I, which are just going to the cylinder, and evolving the state backwards and putting the state I at minus infinity.
So what we're trying to do is on the left hand side of the equation is that state psi, right, which we are writing as.
Oh, here we are writing the operators. These operators are equal to a linear combination of operators here. And in this way, they generate the same state psi here. There is no difference between operators and states. So the fact that operator generated by this will be a linear combination generated by something at minus infinity, so it can be written like that.
I want to just check something about my understanding. If I raise that mu to upper index, that delta becomes delta minus 1, right? Like metric also has dimension here. When you are explaining descendant operators, that mu, if it goes up.
So mu derivative increases dimension by 1. 2 derivatives by 2, 3 derivatives by 3, etc.
It doesn't depend how I take derivative by lower index or upper index, because I feel metric also has dimension here.
No.
Instead of partial lower mu.
No, the partial is correct, the way I wrote it.
But if you had an upper mu instead of a lower mu, would it be delta minus 1?
No, well, why does the metric have dimensions for you?
Because, for example,
Delta ij, dxi, dxj. Dx has dimension, dx has dimension, delta ij is delta ij, it's Kronecker delta.
but if I have, for example, a vector which has dimension 1, so a mu up, a mu down should be a scalar, right? Because when I translate it, I have rho x bar over rho x and an invert of this, which cancel each other.
I mean, what's the difference between upper and lower index? It's just some minus sign for t. I don't know. So for me, they have the same dimension.
Are we in flat space-time?
Yeah, but yeah, maybe we can talk like it.
Yeah. So you can right? The way we are thinking here, we are in flat space. Upper or lower index is just some sign for t. Sometimes here it's Euclidean. There's not even that, right? Here, upper index or lower index is the same. But even if it was not Euclidean, it would be just a minus sign. Now, of course, this is your choice. You could decide that you put in front of the matrix something with units of centimeters, and then you are measuring everything in dimensionless quantities. Then, yes, inverting the metric would give you this 1 over centimeter, but then you are putting a scale by hand in the metric, which you could do, but I'm not sure you want to do in a CFT, probably not.
So metric doesn't have symmetry scaling, right? It's kind of a scalar in terms of symmetry transformation. Because I assume metric also has some scaling.
For me, the metric is what I wrote there, is dx square, right? So dx tilde square is the line element. Dx square is another line element. What do you call exactly the metric there? Is delta mu nu that contracts dx mu? Or do you call it something else?
I call it the thing that multiplies dx, like everything before dx. So kind of be changing a metric by x over 4, right?
Right, but here we are not doing that. Our metric is always RD. Our metric is always dx mu. Right? Our metric, except when we go to the cylinder, in flat space, our metric is dx mu. Okay.
Pedro,
Yeah.
one of the operators in the cylinder on your left should be at the origin, right?
Well, okay, that's a good point. If one of them is at the origin, indeed, one of them is here. Good point, yeah. So the way I wrote the formula, indeed, I put one at the origin, one at x, and then I rewrote as just one, a bunch of them at the origin. I don't need to do it. I can put x, y, and then expand everyone in terms of the origin. But then I would need to put x and y here. Because by translation invariance, I put them at the origin, and then, so then the picture, yes, I should put like this. Is it okay? So it doesn't matter, right? It's the same logic as I said before. The fact that you have 2 points here, or one at the floor and one up here, doesn't change anything I said. Okay. I think I would rather take more questions about this point and stop when there are no more questions. And tomorrow, we will start with this very important equation that I wrote here to finish the review of CFTs plus motivate the tutorial that you will solve in the afternoon. So the basic idea right now, what we would like to do is take this equation, and this equation will now, there will be a set of logical steps, and then we will conclude that delta I and C, I, J, K fix any endpoint function. Right? So this is the plan for tomorrow. It will be start from here and reach that very important conclusion there. But given the importance, the central importance of this equation and this set of logic, I think I will stop here and ask you if you want to try to ask me any other questions on everything we have seen so far.
I have a question. Can you make a little bit more explicit this last map that we have between the state that we get at 0 after we do the evolution backwards in time and the operators to have like this final map between the state and the operators?
So maybe you are asking, do we know something about all these Cs, all these constants here? Could you phrase it?
It's before that. I understand how we have this product of operators and this defines the state, and how we can get the state and define another state at the initial time. But then we do a final map and get this final state at the initial time, and now write the two original operators that we have now as a sum of operators defined just at 0. I guess it's just that making this last step of mapping this state at 0 to operators at 0 a little bit more. Just what we're doing a bit more.
So let me see if I understand. So on the right hand side here, I have a sum of operators, all of them at the origin.
Yes.
So each term here inside this bracket is generating a state. Because I act with this guy at -infinity, I generate a state. I act with this guy at -infinity, I generate a state. I act with this guy at -infinity, I generate a state. So here we already have 3 states. And there are infinitely many in the ... And that's for one primary. Then we have to do it for all the primaries. So in this sum, this is the sum of the CIs times psi's, right? So this is giving a very explicit map saying this generates a sum of CI times the state psi, where the definition of this psi is whatever state the operator OI generates. Then this is as explicit as it is if I tell you what these constants are. So then I think you would agree that your question is there any hope of finding these constants, or it's something formal that I write? Right? Do I write this just for fun, or can I in practice find these constants? Right? This becomes useful if we can fix these constants here, right? So I need to fix this guy, and then this guy, and then this guy, right? If we fix these constants, then this becomes a very explicit equation that tells me given 2 operators, here is the decomposition, right? And so the question here, and that's the main question, is can we fix these constants, C, K, with index mu1 up to mu s? And then the next question would be how to use this equation to show this statement that I said down here. And that's what we're going to do next time. I'm going to show that indeed everything I said is very generic and true, and as Gang complained, it's true more or less always. But what's powerful in a CFT is that we can really get all these constants. And so next time I'll remind you or show you how we can get these constants very explicitly in a CFT, and therefore how we can decompose any 2 operators as a state, right? But now you start already to have a feeling of what's going to happen. If you have many operators, you can take the last two and send them to infinity and replace by 1. But now you have 1 and you have the third one. Now you can take the first and the third and send them to infinity and get 1 again. Right? And now by doing this game, you can get rid of any 4 correlation function and trivialize any correlation function. And that's going to be the game. As soon as we learn how to fuse 2 operators, then we can apply it several times and fuse any number of operators.
So this also shows that maybe we can reduce 3-point functions to 2-point functions.
It could. It could make you think like that, yeah. It's not true. You will see next. Bye.
So, sort of as a follow-up, but it's a bit of a silly question. So, the fact that we can determine any endpoint correlators from 2 and 3-point correlators, is it just purely mathematical here, or is there a physical reason when you're dealing with CFDs that allows you to do that? Because, like, to kind of illustrate my point, I come from a QFT on curved spacetime. We're always dealing with quasi-free states, or Hadamard state. So it's only the 2-point correlator is enough to characterize the state. So I'm just curious from that standpoint.
Yeah. So typically, what happens is that in any quantum field theory, you have equation like this one that I wrote here. In practice, it's useless because you have no way of computing these constants, and they are super complicated functions. So in general, if you have a quantum field theory, this can be an non-trivial function, like the Bessel function that we computed, right? The propagator, right? So we have the complexity of a general quantum field theory where even the propagator is a Bessel function, to a CFT where it's a power law. It's the same thing here. We will see that these C's are all simple power laws. If it was a general CFT, all these C's will be complicated function of all the masses that you would have in your theory, and it's almost impossible to hope that you'll be able to compute them. And so what a CFT gives you is that the kinematics are such that studying the effect of 2 operators and reducing to a single operator, you can do it kinematically. That you cannot do in a general interacting field theory.